Hi, my name is Alisa Godovanny. I'm a grade 11 student at Bill Crothers Secondary School, and I will be helping you solve an example math question for the topic of rates of change in trigonometric functions. A trigonometric function is a function that describes the relation between the sides and angles of a right triangle. This includes the sine, cosine, tangent, cotangent, secant, and cosecant functions. A rate of change is a rate that shows how one quantity changes in relation to another quantity. Rate of changes can be positive or negative. The question I will be helping you solve is number 9 on page 371 in the grade 12 Advanced Functions Nelson textbook. I will now read the question to you with highlighted key elements. Recall in section 6.6, example 3, the situation that modeled the populations of mice and owls in a particular area. A. Determine an equation for the curve that models the ratio of mice per owl. B. Use the curve to determine when the ratio of mice per owl has its fastest and slowest instantaneous rates of change. C. Use the equation you determined in part A to estimate the instantaneous rate of change in mice per owl when this rate is at its maximum. Use a centered interval of 1 month before to 1 month after the time when the instantaneous rate of change is at its maximum to make your estimate. In addition to this, they give you 2 points, the maximum and the minimum point, which is 22, 24.7 and 10, 15.7. The big idea of this problem is to find the equation of the graph given, as well as finding the instantaneous rates of change at different points. The key elements that were highlighted are very important and will help you solve the problem. The question says to refer to example 3 on section 6.6. If you take a look at this example, it shows how the data was collected for this graph and how the ratio of mice to owl was found. The steps for success are to take in the given information, determine an equation for the graph given, write a therefore statement, determine when slowest instantaneous rates of change occur, when the fastest instantaneous rates of change occur, and writing a therefore statement. Use equation to determine what the instantaneous rate of change is at the maximum, and write a therefore statement again. In order to determine the equation, we need to look at the graph and look at which base trigonometric function we will want to use, preferably one where we can get no phase shift. To recall, these are the base trigonometric functions. We will look back at the graph and see which one starts at the 0 on the graph. As you can see on the graph on the y-axis, it looks like a positive cosine function, although if you look closely it is not at the maximum point, so therefore every base function you choose will need a phase shift. Because of this, you can use any base trig function. In this example, we will use the positive cosine function. You can choose any other base trigonometric function, as all the components of the equation will be the exact same except for the base trigonometric function and the phase shift. To start off in finding the equation, we will determine the equation of axis. The equation of axis is an imaginary horizontal line that symmetrically splits the function in half. In this picture, the line is not exact. This value is also equal to the k value in the equation. In order to mathematically get the exact k value, you must take the max point y value and the min point y value. You add these two together and then divide it by 2. This number is directly in the middle between these 2 points. This is also what splits the graph in half symmetrically, while also still being the k value of your equation. You now have one numerical value for your equation, and this is what your equation currently looks like. We will now be calculating the b value of the function. In order to do this, you must determine the period first. To determine the period, you must look at where one cosine cycle is complete. In other words, you are looking for how long it takes for the cosine function to start and end once. Make sure you are looking at the cosine function where the graph is at its maximum point, not in the middle. The positive cosine function starts at 22 on the x-axis and ends at 46 on the x-axis. The difference is 24, meaning the period is 24 months. To find the b value, there is an equation. The equation is b equals 2 pi over the period. Since the period is 24 months, when you divide 2 pi by the period, you get pi by 12 as your b value. For your equation, you now have 2 numerical values. You have the b value and the equation of axis, which is the k value. Next, we will be looking for the a value, also known as the amplitude. The value of the amplitude can be found by finding the difference between the maximum point y value and the equation of axis, or the minimum point y value and the equation of axis. In this example, we found the difference between the maximum point y value and the equation of axis. The maximum point y value is 24.7 and the equation of axis is 20.2. The difference of this is 4.5, meaning the amplitude is also 4.5. You now have three numerical values for your equation. You have your b value, your k value, and your a value. Last but not least, the last part to completing the equation is finding the phase shift. The phase shift needs to be found because in this example, the positive cosine function does not start at y equals 0. In order to find the phase shift, you must simply look for where the positive cosine function starts. Then you must find the value of how much it was translated from 0. In this example, you can see it was translated 22 units to the right. This means that in the bracket, it will be t minus 22. The reason this value is t minus 22 is because it is translated to the right. If it was translated to the left, it would have been t plus 22. Your equation is now complete as you have all of the numerical values needed to complete the equation. Therefore, the equation is r of t is equal to 4.5 cos pi by 12 bracket 2 minus 22 plus 20.2. When graphed on Desmos, this is what the function looks like. Since this function looks exactly the same as the function given in the textbook, we know that our equation is correct. The next part of the question wants us to determine when the ratio of mice per owl has its fastest and slowest instantaneous rates of change. We will start off by finding the slowest instantaneous rates of change. First, when starting off and finding the slowest instantaneous rate of change, you must think logically. Finding the instantaneous rate of change is the same thing as finding the slope of the tangent line. The steeper the tangent line, the larger the slope. So to find the lowest instantaneous rate of change in this question, you must look for a point on the graph where the tangent line is the least steep. In most cases, it is the maximum and minimum point. This is because if you take, for example, the maximum point and draw a tangent line, it will be parallel to the x-axis, meaning it is not steep at all. Due to this, when you find the slope, it will be 0 as the y values are the same. In this example, we found the instantaneous rate of change of the minimum point. In order to do this, you must make a table of values and in your t section on the left side, use a centered interval of 0.001. This means that you take your minimum t value, which is 10, and you add and subtract 0.001 to get the most accurate answer. This gets you 10.001 and 9.999. You then take your new t values and substitute them into your equation that you found in part A. You will get 15.7000015 for both as the r of t. Now that you have these 2 points, you can go ahead and substitute them into your slope formula, which is y2 minus y1 divided by x2 minus x1. You will get 15.7 minus 15.7 divided by 9.999 minus 10.001. Since your two y values are the same, you get 0 divided by a number. If you have 0 on top, your answer will always be 0. Therefore, the instantaneous rate of change will be 0. Since the minimum point's tangent line is parallel to the x-axis and so is the maximum point, then you can assume that the IROC would be the same. We went through the same process and calculations for the maximum point as we did for the minimum. As you can see, the IROC turned out to be the same. This means that for every maximum and minimum point, the IROC will be the same, which also means that the slowest IROC is on all of the maximum and minimum points. For the graph we were given, the IROC is the slowest at 10 months, 22 months, 34 months, and 46 months. We will now determine when the IROC is the fastest. On this graph, there are many points of inflection. This point is a point on a continuous plane curve at which the curve changes from being concave to convex. This point occurs halfway between the maximum and minimum point. This point is usually the point where the fastest IROC occurs. To determine if this is true or not, we went through the same process and calculations for the fastest IROC as we did the slowest IROC. We did this for 2 different points of inflection. For both, we found the IROC to be 1.178. To make sure that we were correct, we chose a random point that wasn't on the maximum, the minimum, or a point of inflection. We found the IROC of this. The IROC was found to be 0.58905. This proves that the fastest IROC is found at the points of inflection. For the given graph, the fastest IROC is at 4 months, 16 months, 28 months, and 40 months. Did you notice that the slowest and fastest IROC occurs every 12 months? This is half a period from the first one. We will now be moving on to question C. This question asks to find the IROC in mice per owl when the rate is at the maximum using a centered interval of 1 month before to 1 month after the time of the maximum. Since the maximum is at 22 months and you need to use a centered interval of 1 month before to 1 month after, our two t-values are 21 and 23. You then carry out the same processes by taking your t-values and substituting it back into the equation to allow you to get your R of t values. You then find the IROC by using your equation of y2 minus y1 over x2 minus x1. As you subtract these, you get 0 divided by -2. Since you have 0 on top, you get 0 mice per owl per month. This makes sense because you are finding the slope of the tangent line at the maximum. Since the tangent line is parallel to the x-axis, the slope is 0, just like it is in the previous question for slowest IROC. Therefore, the ratio of mice to owls at the maximum is 0 mice per owl per month. One career that incorporates this type of problem is stockbrokers. Stockbrokers use these kinds of graphs to monitor performance of stocks and other financial instruments. They would need to calculate the instantaneous rate of change to learn historical performance of investment instruments in order to determine which stocks to invest in. Thank you for watching. I hope you now understand how to create an equation given a trigonometric graph and how to find the instantaneous rates of change at various points.